In this video, we'll learn how to change orbits in inverse square law systems. We'll start off by remembering that the total energy of an orbit is determined by the shape of that orbit. It's proportional to the eccentricity squared minus 1, where the proportionality constant is the coefficient of the central force times the reduced mass divided by twice the angular momentum squared. Imagine I start in this orbit with energy E1. Let's pick a coordinate system for this orbit, so here is our angle theta. Then the equation for the orbit is R1 is equal to C1 divided by 1 plus the eccentricity of the orbit times cosine of the angle theta. What happens if I want to move to this second orbit, which has energy E2? In terms of our original coordinate system, the new orbit is given by R2 is equal to C2 divided by 1 plus the eccentricity of the second orbit times cosine of theta 1 plus delta 2. We picked an initial coordinate system that aligned with the first orbit, but the second orbit might not be aligned with that coordinate system. Then the angle delta 2 measures the offset between the distance of closest approach of the second orbit with that of the first orbit. These two orbits intersect at R1 of theta 0 is equal to R2 of theta 0. We can use this equation to solve for delta 2, and then we use the definition for E2 to solve for the constant C2, as well as the eccentricity of the second orbit and the angular momentum of the second orbit. How should I think about going from orbit 1 to orbit 2? Let's start in the first orbit, and at some point, I'm going to inject some energy into the system by applying a thrust. This bumps us into a new orbit that looks like this. Let's work out what that thrust did to our system. If we start here at velocity v1, then after the thrust, we're traveling at v2, which is going to be some constant lambda times the initial velocity v1. And this relationship is going to have a knock-on effect for all of our other constants. First, the angular momentum, which is the radius cross the momentum, is also going to increase by a factor of lambda because it's just proportionate to the velocity. Since the constant c is equal to the angular momentum squared divided by the force constant gamma times the reduced mass mu, then c2 will be equal to lambda squared times c1, since gamma and mu don't change in this system. In this particular case, I applied a thrust at theta equals 0. That means that the radius of the first orbit at angle theta equals 0 is equal to the radius of the second orbit at the same theta. This gives us a relationship between the two orbits. R1 at theta equals 0 is given by C1 divided by 1 plus epsilon 1. This is equal to the radius of the second orbit at theta equals 0, or C2 divided by 1 plus epsilon 2. Using the value of C2 we just derived, then the right-hand side of the equation becomes lambda squared times C1 divided by 1 plus epsilon 2. Note that the C1s cancel out. Now I have a relationship between the eccentricity of the second orbit, epsilon 2, and the eccentricity of the first orbit, epsilon 1, in terms of the energy I've injected into the system. Then the eccentricity of the second orbit, epsilon 2, is given by lambda squared times the eccentricity of the first orbit plus 1 minus 1. Now I'm going to work through an example of how to change an orbit. We'll start in a circular orbit of radius r1 traveling at a velocity v1, and we'd like to transfer to an orbit of radius r2. We're going to do this in two stages. First, we'll apply a boost lambda 1, which changes our velocity from v1 to vp. This now kicks us into an elliptic orbit, and we'll continue in that elliptic orbit until we reach apogee. Then we apply a new thrust to move us into a circular orbit at radius r2. This thrust, lambda 2, takes us from velocity va, or the velocity at apogee, to the velocity v2, which is the velocity needed to maintain a circular orbit at the radius r2. We'll solve this in 3 steps. The first step is applying boost 1. Then the second step is traveling from the perigee of the elliptic orbit around to its apogee. And the third step is transferring to the second circular orbit. Our goal is to solve for the 2 boosts, lambda 1 and lambda 2, that are needed to make this orbital transformation. Under boost 1, the radius of the circular orbit, r1, is equal to the minimum radius of the elliptical orbit. So that tells us that r1 is equal to c divided by 1 plus the eccentricity of the orbit. The velocity at perigee vp is equal to lambda 1 times v1. and the coefficient of the elliptic orbit c is equal to lambda 1 squared times r1. By substituting this value for c into the equation of the two orbits meeting, we find that r1 is equal to lambda 1 squared times r1 divided by 1 plus the eccentricity of the orbit. Here the r1's cancel out. We can now write the eccentricity epsilon as lambda 1 squared minus 1. Next, we'll continue in the elliptic orbit until its apogee. The apogee of this orbit corresponds to the radius of the second orbit. So we can substitute the values for c and epsilon that we just worked out. And we find that r2 is equal to lambda 1 squared times r1 divided by 1 minus lambda 1 squared minus 1. Now we can solve for lambda 1 in terms of the two radii, which are givens in our problem. And we find that lambda 1 squared is equal to 2 times the radius r2 divided by the radius r1 plus the radius r2. Lastly, we'll do a boost at the apogee that bumps us into the final circular orbit. During that boost, we'll scale our velocity at apogee by some constant lambda 2 to reach our final velocity v2. Because we've changed our angular momentum during this boost, r2 is equal to lambda 2 squared times c. Since r2 is equal to the distance of the elliptic orbit at apogee, that tells us that c divided by 1 minus epsilon squared is equal to lambda 2 squared times c. The c's cancel out, and we're left with epsilon is equal to 1 minus lambda 2 squared. But we already worked out a relationship between epsilon and lambda 1. So we can substitute that in as well. Since we now have a relationship between the second boost, lambda 2, and the first boost, lambda 1, which we've already found an expression for in terms of our two circular radii, we can now write an expression for the second boost in terms of those radii as well. And we find that lambda 2 squared is equal to twice r1 divided by r1 plus r2. This tells us how big our boosts need to be in order to successfully transfer from a circular orbit at radius r1 to a circular orbit at radius r2. Lastly, we can work out the total change in speeds of the orbits. If we start at velocity v1 and boost by lambda 1, we end up at the velocity at the perigee of the orbit. Then as we travel in the elliptical orbit, we go from the velocity at perigee to the velocity at apogee. And we know that since angular momentum is conserved during the orbit, we can write the velocity at apogee as r1 divided by r2 times the velocity at perigee. And finally, when we're at apogee, we apply the second boost, lambda 2, to get to the final velocity of our second circular orbit. We can combine this all together to find that v2 is equal to lambda 2 times the velocity at apogee, which is r1 divided by r2 times the velocity at perigee, which is equal to lambda 1 times our initial velocity. So when I plug in the definitions for lambda 1 and lambda 2 that we worked out, we find that the velocity v2 is equal to the square root of r1 over r2 times the velocity v1. And I'll leave it as an exercise for you to work out whether this agrees with the Newtonian definition of the velocity of a circular orbit. Thanks for watching, and I'll see you next time.